Chapter 10, we're moving into new territory and talking about fluids. We have quite a bit to cover this chapter. We're going to first start with talking about the phases of matter, solid, liquid, and gas. Introduce the concept of density and specific gravity, which is a property of all matter, solid, liquid, and gas. Then we're going to move into talking about fluids, the liquid and gas phases of matter. We'll talk about how pressure exists in fluids and what atmospheric pressure is. Pascal's principle describes how pressure behaves in a fluid. Talk about how we measure pressure in the atmosphere and in fluids. Buoyancy and Archimedes' principle is a very important concept. Then we're going to move on and start talking about fluids in motion and how fluids tend to flow. And Bernoulli's equation is a very important principle for talking about fluid flow. And then the remainder of the chapter is looking at applications of Bernoulli's principle and the flow of fluid through various things, through the air, with baseballs and airplanes, blood flow. Talk a little bit about viscosity and having friction in the fluid flow. And then just look at a couple more applications for flowing in tubes and pumps. The three phases of matter that you're probably already mostly familiar with, solid, liquid, and gas. Just some basic definition. A solid is going to have a definite shape and a definite size. My table right here has a definite shape and a definite size. It is definitely solid. A liquid is going to have a fixed amount of volume, but can be any shape. Right, you can take water and you can slosh it around in your glass or in your water bottle, so the shape can be essentially kind of fluid. So we're going to describe a liquid as being fluid. It is going to have a fixed volume. What that means, it is not going to compress, at least not very easily. So that's why it hurts when you do the belly flop off the high dive, because the liquid tends not to compress underneath of you. A gas can be any shape, and it can be easily compressed. So it does not have a fixed volume, and it does not have a fixed shape. Both liquids and gases are going to flow, so in this chapter we're going to consider both of them as fluids. The density of an object is an intrinsic property of each object. It's going to depend on essentially the atomic structure and the atomic makeup, how many protons and electrons are inside of an atom or inside of a substance, and how tightly they're packed together. We're going to define the density with this Greek symbol rho, and that's going to be an object's mass divided by an object's volume. SI unit for this guy is going to be kilograms per meter cubed. So if you're ever working a problem with this, keep in mind that volume has to be in meter cubes and mass needs to be in kilograms. Occasionally you'll be given things in grams and centimeters. Please make sure you convert. You may also be familiar with volume being in gallons in the US system, or maybe in terms of liters. If you drink a 2-liter bottle of soda, remember that 1 liter is 10 to the minus third cubic meters. So you might need to convert from liters to cubic meters in this chapter. Water at 4 degrees Celsius has a density of 1,000 kilograms per meter cubed. Pretty nice that it's a factor of 1,000. Something that you'll see in the bio and med fields is going to be an object's density relative to the density of water. We essentially just take the ratio of the density to water. You also see that if you ever brew your own beer or make your own wine. So now let's look strictly at fluids. So that would be the liquids and the gases. We know that fluids are going to have some pressure associated with them. If you've ever squirted a garden hose or jumped underneath of, gone pretty deep under a pool, you can feel that there's pressure on you. We're going to define pressure to be the force per unit area, and that's going to be a surface area. One thing to note is pressure is going to be a scalar, and the units for that guy is going to be a Newton per meter squared. Newton comes from force, meter squared comes from area. This has a special name. It's going to be called a Pascal, written by the uppercase P, lowercase a. So you're going to see pressure have units of pascals, where 1 Pascal is 1 Newton per meter squared. And one thing to think about is pressure is going to be the same in every direction in a fluid for a given depth. What that means is if I take a little chunk of fluid right there and I say, let's take a look at all of the pressures that are on that guy, it's going to have some pressure from that direction, it's going to have some pressure from that direction, it's going to have equal pressure from that direction, that direction, that direction, as well as that direction. And if the pressure wasn't coming from all of the directions, suppose I took away that pressure right there, if I take away that force, then this fluid is going to tend to flow upwards. There's no force in that direction, there's no pressure. And we know that this glass is just sitting here, it's not going to spontaneously start flowing, so pressure must be the same in every direction in a fluid. Where the fluid comes into contact with the walls, a wall can only exert a force that's going to be in the perpendicular direction. A wall cannot exert a parallel force, much like the normal force for solid surfaces. If the surface was exerting a force in the parallel direction, then this little parcel of water would tend to move upwards, and you would have the fluid flow kind of like that. And this jar is just kind of sitting here on the table. We know that it's not going to spontaneously start flowing. So surfaces cannot exert a parallel force on a force parallel to the surface. They can only exert a perpendicular force. Let's take a look at how pressure behaves in fluids. You know, if you've ever gone to the deep end of the pool, that you get more and more pressure on your ears the deeper you go. It turns out that we can write this pressure as a function of the depth h, and essentially, if you consider drawing a box in the water, it's got a certain volume, and you consider, the bottom surface right here, that area right there, it's going to have the weight of all of the water above it pressing down on it. That weight is going to apply a force or a pressure to that. We can figure out what that force is. That force is simply going to be the weight of the water, which is going to be the mass multiplied by the gravity. We can use what we know about the density and the volume to rewrite the mass simply as being the density of water multiplied by the volume of the cube, so it's going to be the volume of this entire cube of water, which we can also say that the volume of that cube of water is going to be the bottom area multiplied by the height. So we're going to have the density of water, and now we're going to have the area times the height representing the volume. So that's going to be the force that is being applied to the bottom surface. If I take that force and I put it into my expression for pressure, you can see that the A's are going to cancel out, and I can write my pressure being simply the density times the gravity times the height, or how deep I am. You may occasionally see that written as d for depth. This is true as long as density is not changing with depth, which will be the case for everything we look at in this chapter. The same thing is also true for the atmosphere, which is a fluid. If you consider all the gas that's in the atmosphere, and here we are down here at the surface, all of that weight is also pressing down on us. So we're going to have some pressure due to the atmosphere, and that's going to be 1.013 times 10 to the 5th pascals, and that's simply the weight of the atmosphere pressing down on us. Also see this occasionally written as 1 atmosphere. Another unit of pressure is going to be the bar. You might be more familiar from the Weather Channel as seeing that the pressure is going to be 1,000 millibars. So that's more typically used in weather. for everything we do in this particular class, of course, we need to work it in pascals. Another unit that we'll talk about in a couple of slides is going to be millimeters of mercury. So lots of units we can consider. Again, always work it in pascals. It turns out that this is going to be about 14.7 pounds per square inch. That's quite a bit if you think about the surface area of your body. That's your surface area of your body is going to have quite a few square inches. All of this pressure does not crush us. We're used to this pressure pressing against us, and essentially our cells are going to maintain an internal pressure that balances it. However, if you go deeper and deeper into the ocean, then you get more and more pressure and it becomes harder for your body to balance. Because we live in this atmosphere where there is always one atmosphere of pressure pressing down on us, we typically want our pressure gauges to read 0 with this one atmosphere. It would be kind of funny to go around and always see that the pressure that you measure is going to be 1. We always like to define that to be 0. So we introduced this new concept called gauge pressure, which is essentially we're taking away the atmosphere. So if you measure your tires, you're going to be measuring the pressure of the atmosphere plus the pressure of the tires. You're going to be measuring some absolute pressure. Right there, it's going to be a pressure absolute, but what the gauge is going to read is going to have the atmosphere taken off. So if you read the pressure gauge on your tires, it's so many pounds per square inch. Suppose that it reads 2.2 atmosphere, then the absolute pressure in your tires is going to be 1 atmosphere. Plus that, the absolute pressure in your tires is going to be 3.2 atmosphere. However, what the gauge actually reads is going to be 2.2.